So here we're going to plot the original system unmodified, normal damping coefficient, spring stiffness, and of course the forcing function. So we'll set it, plot it, and it turns out to be pretty much what it is supposed to be with our software, and we'll launch a simulator. So as you can see, the 0 is where the equilibrium position would be. And it goes to 1 because, of course, it's a unit step function, and yeah. So that's case 1. So here now we're going to do the second case where the spring stiffness is larger than the nominal value by one order of magnitude. So we'll, vertical system, set the forcing function properly, and let's plot it. And yes, that's already it up there, and we'll do the simulation. As you can see, it's quite fast, the oscillations, and many of them. So now we're actually going to decrease the stiffness by an order of magnitude less than the original system required, so 1600. And we'll set the forcing function, plot it, and let's simulate it. So that's much smoother, of course, than the high stiffness, as you can see. Now we'll do the next case where we're actually going to put the stiffness back to the nominal value, and we'll set the damping this time to be higher than what it should be, so 16,000 kilograms per second. Set it vertical system, initial position of 0, and plot it first. We'll plot it first. Okay, so you can see that it looks to be similar to the low stiffness case, but as you can see, it moves up to the equilibrium position actually pretty fast, and it's quite jerky. As we'll see it one more time. See how fast it moves up. And for the last case, we're going to lower the damping to just 160 kilograms per second, which is lower by one order of magnitude than the nominal value. Let's plot it. So it looks to be quite long. Hasn't settled yet, so we'll go to 20 seconds. Okay, and that's actually the longest that our program can run for, so let's simulate it. So oscillations seem, they're not super fast. They're kind of smooth, but there's obviously way too many oscillations.